Okay, folks, before we proceed on to the great and glorious things like the hydrogen atom, I need to teach you more integration. So we will be integrating in multiple dimensions and in various curvilinear coordinates. The reasons for that is that, well, most things are multidimensional. And in particular, you will see that in thermodynamics, where your parameter spaces are very rarely one-dimensional. You would have some pressure, some temperature, and some volume, and the trajectory of your system as it's being compressed, expanded, heated up, and so on, is a curve in multiple dimensions. Now, you would normally need to calculate, for example, the change in internal energy or the work that's been done by external force, or the change in entropy as the system proceeds on the trajectory, and that is usually an integral. Now, so today what we will be looking at is the corresponding mathematical object. It's called a line integral in multiple dimensions. But before that, I will remind you the definition of Riemann integral. Remember when we were calculating our areas under curves, we were partitioning the integral with x and that's x, some function. We were creating these little slices, and the width of each slice was delta x, and then we chose some points inside those slices, delta x. And then we choose some point psi, and this is f of psi k, and that point is psi k. And we were constructing the sum over k f psi k delta x, and if delta x had different sizes, we could also call the delta x. And then in the limit, when this partitioning becomes finer and finer and the number of points becomes greater and greater, so limit delta x going to 0, or equivalent is the number of these partitions going to infinity. If this is point A and that is point B on the x-axis, that was the definition of the integral from A to B f dx in the Riemann sense. And then I think it was in the first semester in Chem 1034 that I have proven the Newton-Leibniz formula that connects that to the antiderivatives, and then we have an infrastructure that allows us to integrate. Now let us now move this exact situation to multiple dimensions, starting with 3. So that's our three-dimensional plane. That is x, that is y, that is z. And let us consider some trajectory in the xy plane. So let's say something is moving on this trajectory within the xy. And then there is a function of x and y, so our z would be f of x and y. That is a function of whatever coordinates we have. So somewhere here, there's a curve that is the function. Okay, and our task is to find the area of the fence, so to speak. So if we drop points vertically, like that, we will have a kind of ribbon extending in 3 dimensions. This will be our point A, and that will be our point B. And then we will parameterize this trajectory as x, being the x of time, and y being y as a function of time, and possibly more. So we can have multiple dimensions, and the trajectory of the point is the function of time within those multiple dimensions. And we would like to know what is the area of that fence, and we will define it in exactly the same way as we have defined the Riemann integral. So we will select a partitioning of this. We will call each little element here delta S, the length element of that curve, called delta S. Okay. Inside each interval, we will pick some point C, okay, and this point over here will be F of X, K, Y, K. Okay, so let us do exactly the same and sum up the areas of these little intervals and then see what we can do about it. So we will have a sum over all of the intervals delta S, F of X, K, Y, K, corresponding to this location CK, delta S, okay, and we will take the limit of this as delta S, K, to 0. This is the line integral, so an integral, and we will call this line gamma. And an integral is called gamma f of x, y, ds. So notice that what was previously dx now became ds, so that's the element of this path. And we have the f of x and y. Now, how do we take such integrals? Well, the first thing we need to do is to consider this element ds, because f of x and y is fairly clear, right? We could just substitute our parameterization, and this would simply become a function of time. Now, question is, what is ds as a function of time? Because this curve can wibble and wobble, and of course at different moments and in time the length of that interval might be different because, well, the particle might just suddenly accelerate. Right? So let us take a look at what is ds. Well, we have our x and y here, and we can just look at it geometrically. If we look at that element from the top, we will have the curve segment ds, and this is dx, and that is dy. And it stands to reason that ds squared is dx squared plus dy squared, just Pythagoras' theorem, simple triangle. Okay, so using that, ds squared is dx squared plus dy squared. And if we had multiple coordinates, not just two, this would have continued. So we can just write dot, 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 and so on. But of course, dx and dy we know because they are functions of time. So if we have here dx by dt equals x prime of t, then dx is x prime of t dt. We can simply just substitute that in. So we then have x prime of t dt squared plus y of t dt squared. Dt can be taken out. We will use the Leibniz notation for the derivative. So dx by dt squared plus dx plus dy by dt squared dt squared, and possibly other variables here and here. Well, let's just now take the square root, and then we are done. dt can be taken out of the bracket, and so the result is that dx is square root of dx squared plus so on dt. And that's the transformation of the length element for the curvilinear integral. And once we have moved to the variable t, so x is a function of time, y is a function of time, ds is now made a function of time because these are functions of time and that is just time. We are back to our standard one-dimensional integral with respect to time that we can take. So, examples. In your handout, an integral over a curve x, y to the fourth ds, where x of time is 4 cosine t, y of time is 4 sine t, so some kind of circular motion. The x-coordinate is a cosine, the y-coordinate is a sine, and time here runs between minus pi by 2 and pi by 2. So a half circle. So we have a half circle circular motion. We have something that depends in this way on the x and y coordinate of the point. And now we need to do the calculation. Well, okay, we can just do a direct substitution. We know what is x, we know what is y. Let us find us the ds. As per that root over there, dx by dt is minus 4 sine t, so that will be 16 sine squared t. dy by dt is 4 cosine t, so plus 16 cosine squared t dt. Well, sine squared plus cosine squared is 1, root 16 is 4, just 4 dt. So the path is incremented 4 times faster than our time because of that. Okay, so our integral is now an integral. Time runs from minus pi by 2 to pi by 2. X is 4 cosine t. Y is 4 sine t, so 16 squared is 256. Sine to the fourth t. And then another factor of 4 here. T. Okay, so that's 256, 512, 10, 24, 496. We all remember our powers of 2. Integral minus pi by 2 to pi by 2 cosine t sine to the fourth power t dt. And after we do all the tedious arithmetic, we get 8192 over 5. I will not bore you with this trigonometric integral. Okay, so what was this? We can take a look at it from the side at that segment there. X, y, and this is x, y to the power 4. We have a circle of radius 4 and time goes from pi by 2 to pi by 2. So initially, when time was minus pi by 2, the x-coordinate was 0 because cosine minus pi by 2 is 0, and the y-coordinate was minus 4. So we begin somewhere here, and that's minus 4 on the y-axis. Then as time gets incremented, cosine becomes positive and sine is reduced towards the positive axis, and so we have this curve here until we hit plus. And then the function that's in here is linear with respect to x and quadratic with respect to y. So it is something that slopes linearly in z direction, slope 0, and something that grows quite rapidly with respect to y. So if we are, for example, here, then we would have a fixed offset with respect to x and a quadratic curve with respect to y. So it's a very complicated type of fence whose area we are calculating, but that's basically the geometric picture. So we've got this trajectory in the xy plane, and then we are integrating the function that is somewhere here in the third dimension. Let's look at something three-dimensional. So there we don't have such an easy way of plotting the graph, but the mathematics remains exactly the same. So the next problem in your handout, we are evaluating x, y, z, ds over another curve, gamma, and the curve is a helix. We have x of t equals cosine t, y of t equals sine t, and z of t equals 3t. So essentially x and y have circular motion at the same time as z simply increases linearly. This is a spiral in 3 dimensions. And time here rounds from 0 to 4 pi. Okay. Now I will not try to draw a helix in 3 dimensions. You can all visualize it. Let us just do the formal mathematics. Our ds again is root dx by dt squared, so cosine squared becomes, the sine will be differentiated and then sine squared, so sine squared t, plus sine derivative is minus a cosine, plus a cosine, then we square it, so it's a cosine squared, and then 3 becomes 9, and that is dt. So we have root 10 dt for our area element. Okay, and now the integral. So x is cosine t, y is sine t, and times 3t times root 10 dt, and the integral goes from 0 to 4 pi. And once we collect all the constants out, 10, that's half the sine of a double angle, so over 2, and then integral from 0 to 4 pi sine 2 t times t dt. Again, integration by parts in this case, followed by straightforward integral of a sine. I will not bore you with the technicalities. Minus 3 pi over 10 is the resulting integral. Okay, now we have looked at an integral of what is substantially a scalar function. These are called line integrals of the first kind. Now, it is quite often the case that you are calculating such integrals of functions that are not scalar valued and whose value along each dimension may be different. So let me give you an example. So this was integrals of the first kind. So that was 1, that was 2, so 3. Line integrals of second kind. And examples abound in thermodynamics. Remember your expression for the internal energy. It was T ds minus p dv. So some thermodynamic system is being compressed, the volume is reduced, and some Maxwell demon is sitting there and changing the system's entropy. Your task is to find the change in the free energy as a function of some path that the system is taking in those orbits. But whereas previously our path was a function of just time in here, that then fed into the corresponding coordinates, it was always ds, right? So increment of the path. Now we have two independent increments, one of entropy and the other of volume. Another example of this, so if we take an integral of that, so the change delta u will be an integral over some curve in the parameter space t ds minus p dv. So where do we even begin calculating such things? Then you all remember from your basic physics that the work done by a force as it moves the object through a length L is F times L. And if the force is a vector and the displacement is another vector, then it's a scalar product F dot L. And if the path is infinitesimal, then this is F dl. So the total work done by a force, in thermodynamics this will be against the atmosphere, that's pushing us back at actually very considerable pressure, right? Atmospheric pressure is 10 tons per square meter, quite significant. You must have seen the Martian film, right? The Hollywood film. There's only one inaccuracy in that film, which couldn't have been possible in reality, and that's just patching up the hole with the polyethylene that he did. I mean, not under terrestrial pressure. 10 tons per square meter would just blow it out. Anyway, so when we are looking at how the system pushes back the atmosphere, we are dealing with the following thing. It's dw as the infinitesimal increment of work is F vector scalar product dl. So that's our current force and that's our elementary displacement under it, and the result is the increment in the work that's done by the function. And then the actual work will then be an integral of that over some curve in the parameter space, and we will have the x component of x, y, z times dx. That's the x component of the force times the displacement along the x. But of course there are two other components here, so we will have y of x, y, z, y plus z, x, y, z, z. So we need to teach ourselves to take integrals of this type. Thankfully, that is also quite straightforward, because once again the trajectory will be parameterized to us, most often as a function of time, but in general as a function of any convenient parameter. So what would normally be provided is x as a function of time, y as a function of time, and z as a function of time. And the only thing we need to do is to reduce this entire horrible integral to an integral just with respect to time, or with respect to whatever parameter has been provided to us. So, for example, in this case, or maybe for the brevity purposes, let's just take a two-dimensional one, otherwise it's too much writing. So an integral c f of x, y, dx plus g x, y, dy. So the most general form of such an integral in two dimensions. If we know x, then we also know dx, because dx will be dx by dt, right? We just literally multiplied and divided by dt, and then we interpreted this as a derivative. So in here we will have an integral f of x of t and y of t, and then dx by dt plus g of x of t and y of t times by dt dt. And once again, the integral has reduced itself to being an integral that we know how to take with respect to just time, and this will be for some interval from t1 to t2 that makes those coordinates span our entire trajectory. So let's go for an example from thermodynamics, and let's calculate the change in pressure across a realistic trajectory for a realistic chemical system. So, example. Let's say we have an ideal gas and we've got dP is in Vt coordinates dP by dV with the time held constant dV plus dP by dt with volume held constant dt. So the people who teach you physical chemistry will teach you this really horrible notation. I hate these messy indices and so on. But we basically have an ideal gas here. So it's dP equals T. For, I think we've got a mole of it. Yeah, 1 mole of an ideal gas. So N is equal to 1. Okay, so we have our pressure and we want to calculate the change in pressure over 2 different trajectories. So we will take one of them where volume is 1 plus T, so it changes linearly, and temperature is 300 plus 100 T for T from 0 to 1. So essentially we have the volume of 1 cubic meter rising to 2 cubic meters linearly, and at the same time the temperature going from 300 Kelvin to 400 Kelvin linearly. Now notice that the volume is increasing, but so is the temperature. So quite what happens to pressure is not terribly clear, right? That would reduce pressure, that would increase pressure. So let us calculate the change in pressure over this linear trajectory in the parameter space according to the rules that we have just derived. Now notice that this is actually exactly that. dP by dV we know, we can calculate it right now from the ideal gas law. The same goes for dP by dt. As soon as we do that, these are just functions of v and t, and that becomes an instance of that integral, except with slightly renamed coordinates. So let us do that, but let's first clear out some space. Now, there are 2 types of functions, as you hopefully by now know in thermodynamics. There are functions of state, such as internal energy, Gibbs free energy, entropy, and so on, whose change does not actually depend on the trajectory that we take through the state space. There are other functions like work and the heat supply that actually do depend on how we traverse the state space. And this is a subject of much optimization effort in, for example, chemical engineering, where we would like to achieve a given objective with the smallest expenditure of energy that is supplied to the system and with the least amount of waste in terms of the heat that's dissipated outside. And this is where such integrals make an appearance. Okay, let's calculate the corresponding partial derivatives. So our P is nRT already. So dP by dV. Well, it's kind of a definition of a partial derivative that all the other variables are supposed to be constants, but the people in thermodynamics, they still like to write these indices to remind themselves which parameterization they use for the state space. It needn't just be temperature and volume, it could have been entropy and pressure or something like that. Anything that defines the system state completely. So for us, this is minus nRT over V squared. and then dp by dt is just mr. Okay, so substituting that in, you will have dp equal to minus nRT over b dv plus nR over b dt. And we would like to integrate it over this curve, and we will call this curve gamma. Again. So our change in work, however in pressure it is, delta P will be an integral over the curve gamma minus nRT over b squared b plus nR over b dt. Well, we follow the recipe. We simply substitute the differentials for the differentials of our trajectory. So dv is just dt, and dv, d temperature, is 100 dt. So plugging both in, and also substituting volume and temperature as corresponding functions of time. You have them there. It will be an integral, this time with respect to time, from 0 to 1. And then in the brackets here, minus nR. Our temperature is 300 plus 100 T. Then our volume is 1 plus T squared. And that's the first term, and then dv is just dt. dt plus nR in the numerator, then 1 plus T in the denominator, again dt. And well, this is an integral that we do know how to take. So if we go through the motions in here, I will not bore you with taking straightforward integrals. This is minus 100R. That's the change in pressure. It is negative, and you can understand why it is negative, because volume doubled, meaning that all other things being equal, pressure has halved, but then the temperature has only gone up by 30%, so the pressure has lifted by 30%. So first it halved and then it lifted by 30%. The overall change is negative. So that is our change in the pressure. Okay, let us now do it differently. Let us take a trajectory that is no longer linear. Our previous trajectory had been like that. If this is our temperature and that's our volume, volume had been 1 cubic meter, it became 2 cubic meters. Temperature had been 300 Kelvin, it became 400 Kelvin. And we basically took a linear path through the parameter space, from here to here. Let us now take a different path. Let us make the volume change linearly, but the temperature quadratically. Result will be that we've got a trajectory like that. So this blue trajectory will be, volume is still 1 plus T, but the temperature is now 300 plus 100 T squared. Notice that the start and the end point are still exactly the same, but temperature now changes as a quadratic rather than a linear function. Well, actually not much is going to change in our integral here. The only difference will be is that the expression for dt will change, because we are now traversing a curvilinear segment, so it will be a different derivative. And when we substitute the temperature everywhere else, the formula will change. So our new delta V will be an integral still from 0 to 1, because that's the range of our time. And then, okay, minus nRT over V squared dV minus nR. Then the new expression for temperature, 300 plus 100 T squared over 1 plus T squared. And dV is just dt. And then plus, and here we will have different things. So it will be still nR in the numerator, volume in the denominator, plus T, but in this case dt is 200 T dt. Right, that derivative of that, so the transformation of differentials, that prime is 200t and then it's 200t dt. So in here we should actually have had 100 times 100 dt. So in here we will have 200t dt. Again, after we've taken the integral and after the dust has settled, we will have exactly the same 100r as common sense demands. It really shouldn't matter so long as the starting and the end point are the same for the ideal gas, which path we have taken for the parameter space. And when you are doing these things and somebody says, okay, volume has doubled and the temperature has gone up from 300 to 200, none of you ever bother about calculating exact path integrals in order to find out the change in pressure. You just take the starting and the finishing point, and this is it. And in fact, that is just a rigorous mathematical statement that the change in pressure here is not a function of the path that we have taken. You will see multiple functions in your thermodynamics course, notably work, for which this is not the case. And this is why some internal combustion engines are so much more efficient than others. That is because by designing the combustion engine, you are actually designing the path that your system takes in PVT space as combustion takes place, and then you can harness it better and harvest more of the energy at the output. Okay, the summary. We have taken the usual definition of the Riemann integral, which is the limit of the sum of these little rectangles, and we have extended it to multiple dimensions, where the fence, which was here straight, is now curved. What we needed to do for that is to make a correction for the curvature of that fence. That is, the length element ds is now not just dx, it's ds squared equals to dx squared plus dy squared, standard trigonometry here. If we have our coordinates parameterized somehow, usually with time, it is straightforward to calculate ds. So ds squared is dx squared plus dy squared plus whatever else. dx is just x prime dt, so take out the squares and take the root, substitute ds, substitute x, substitute y. The result is the integral with respect to just time, which you know how to take, and that is the curvilinear integral of the first type, when we only have one path coordinate ds. Some example of that. Now, in thermodynamics, you will have situations like that, where you have multiple functions, different functions applied to dx, dy, and dz. And that's one example. That's another, in which case, again, you do exactly the same transformation. You take your trajectory that's parameterized by something, replace the f, replace the g, calculate dx, calculate dy as a function of time and its increment, plonk it all into the integral, get an integral with respect to just time, take it in the usual way. And that's your example of how pressure changes. Standard ideal gas law, change in pressure, standard partial derivative differential for it with respect to that. That's trajectory number 1, that's trajectory number 2 over there. Substitute, transforms the differentials, gets the integral with respect to just time, takes the integral, quite a long story in here, but nothing that you cannot handle by now, get the change in pressure and observe that it is indeed trajectory independent. Okay, so the next lecture will be genuine two-dimensional integrals, not over curves in multiple dimensions, but over volumes in multiple dimensions. Then the lecture after that is about various curvilinear, bent spherical, cylindrical, and so on volumes. And then you both are ready for quantum mechanics. Any questions?